From the 1760s to early 1800s, humanity underwent a large transformation that saw the production methods of many products transition from hand manufacturing to machines, which would come to be named the Industrial Revolution. With the Industrial Revolution came a large increase in demand for structures that could house these materials and machines, and so rose the significance of industrial buildings. Over time, the construction methods of industrial buildings have advanced, allowing for a wide variation of possible designs. Portal framing and sawtooth framing would have to be the most popular. To select the members that will be used in construction of an industrial building, the loads must first be evaluated to determine required strength of each member, including, though not limited to, dead load, live load, and wind load. Dead load is a constant weight that does not alter, as it is the building's self-weight, entities that are permanently attached and cannot be moved. Live load are non-permanent entities able to be moved in and out of the structure, such as people and furniture that is not fixed. Finally, exerted wind force of the building surfaces are measured in wind load. For this project, certain specifications were provided to design the structure of a domestic shed, including determining the design loads, designing purlins, a typical sidewall girt, bracing layout and elements, a typical column, and a typical rafter. The areas are first calculated for the purpose of calculating cladding and insulation. Purlin and girt spacing is selected with a maximum spacing provided in cladding manufacturers' design tables. Purlin selected during the initial stage was a double-lapped span Z20019. Wind load can be calculated using various software, though in this case was done by hand. To calculate wind loads, a wind class of N4 was discovered using details provided of the structure. The design gust wind speeds are then found using the wind class, giving the serviceability limit rate and an ultimate limit rate. Wind pressure is then found. The dynamic gust pressure is calculated and multiplied against the net pressure coefficient. These calculations provide the wind pressure. Ultimate wind pressure of purlins was 2.23 kilopascals, while ultimate wind pressure of girts is 0.87 and negative 0.75 kilopascals. To design the purlins and girts, the dead load and live load of the surface must be calculated. A girt and purlin is selected to use. Load combinations are calculated with the critical load combination being applied to the length of the girt or purlin, providing the force in kilonewtons per meter, which can be compared to the capacity tables to check the selected member is structurally stable. The serviceability is then calculated. Results found that serviceability loads were adequate for a Z25024 girt and double-lapped Z20019 purlin. Roof bracing must be designed before wall bracing. This is done by first calculating wind pressure and suction on the frame. Once discovered, critical tension and critical compression is then calculated, and as a result are given an adequate bracing design and strut design. While these calculations can be done by hand, the program Space Gas has been used to simplify the process of bracing design. In this case, the results found were one wall's bracing design could be a 50 by 50 by 3 equal angle, able to withstand 68.9 kilonewtons of force. Strut design could be 168.3 by 4.8 circular hollow section at 34.7 kilonewtons maximum force, or a 75 by 75 by 2 square hollow section at 23.7 kilonewtons. The bracing design must be able to withstand 27.62 kilonewtons, therefore it is adequate. The strut design must be able to withstand 16.57 kilonewtons of force, therefore both of the design options are also adequate. For the second wall, bracing design selected was a 50 by 50 by 3 equal angle at 68.9 kilonewtons maximum. That must withstand 53.44 kilonewtons of force, therefore this one is also adequate. Rafter design consists of firstly calculating dead load, live load and wind load, then calculating these figures into load combinations for the critical load. Once completed, rafters are then designed for pure compression to avoid buckling of members. Moment capacity, serviceability and maximum deflection are then checked to ensure rafters chosen are satisfactory for the structural requirements. 2 rafters were designed, one that would go in the middle of the structure and one that would go on the edges of the structure. For the middle member, a 360 universal being 44.7 was found to be the best fit. For the edge, 250 universal being 37.3 was the selected member. Column design process is similar to rafters. First, loads are calculated and placed into critical load combinations. Columns are then designed for pure compression, followed by ensuring moment capacity, serviceability, and maximum deflection qualities of the chosen columns are adequate. Through completion of this project, we have acquired valuable information and practice on how to determine wind load and design purlins, girts, bracings, rafters and column members of a structural building. Further information was learnt from our site visit as a class to Building N of the university's Mawson Lakes Engineering Department. During this site visit, an in-person visual analysis and discussion was undergone of members involved in portal framing, including design flaws observed. All in all, Mawson Lakes site visit helped gather a better understanding of how loads are distributed through a structure's members, and this assignment provided information on how these members are designed.